Hello everyone, welcome back. Welcome to my new office. It's very similar to my old office, but it is new. I did move. So today I have something kind of fun and casual to do because I have been working on a video for y'all and it is taking me so long. And so rather than wait another month or two to finish that video, I thought I would do this. So today we're just going to have some fun messing around with REBOUND, which is an n-body simulator that I have talked about before on this channel. I used REBOUND for pretty much all of my research during my PhD and I miss it. I don't get to use it anymore, so let's do that. Okay, so I am on my Windows computer, which I don't usually use for coding. So we'll see how this goes. I don't even know. I'm pretty sure I have REBOUND installed on this. Let's check. Good. I do have REBOUND installed. So I think in the last video I made about REBOUND, which was like years ago, I talked about how to install it and stuff. But basically, if you know how to use Python, it's very simple. You can just pip install it. I'm not sure if you can conda install it. Probably can. Sorry. Computer using glasses. What are we actually going to do in REBOUND? Maybe I should have thought about that before I started recording. I think I kind of was thinking we could do TTVs, which would be really fun, but I also have not yet made a video about TTVs, so that might not make the most sense. I did binary planets in a video just last year, so maybe not that. Oh, okay, I have an idea. So I'm a writer and I am working on a science fiction series and I'm still in like the world building phase, and I could start planning out those systems and make sure they're, good systems, that they're stable. I write both fantasy and science fiction. People like to ask if, where they can find it. You cannot. None of my books have been published yet. I have had a couple of short stories published. I guess I can leave links for those down below. Actually, I think some of them are out of print. Okay, so this is one of my writing notebooks that I do some planning in. So you can see here, there's like going to be these colony worlds, and I have planned out their names, the year they're founded, the stellar type of their host star, and then if it's a star visible from Earth, what that's called here on Earth, and then how long their day is and how long their year is. Y'all, I'm such a nerd. And then for each one of these planets, I have like a little page going that has details about it. And here it has some more info about the star, its stellar mass, its temperature. Then I wrote out where the habitable zone would be for an Earth-like planet, and then where that planet is actually at. And then I did the math on what this period would be, and did that in different units because, there's a standard year and then their own year. I also worked out the timescale for tidal locking because some of these planets are on M dwarfs, so they would probably be tidally locked, and I wanted to make sure that I was taking that into account. I sound crazy. I do sound crazy, but this is fun to me, so. Okay, so let's go ahead and simulate one of these systems. Basically, I already know about the habitable planet in the system, but most systems tend to have multiple planets, and I want them to have multiple planets. So, what shall we do? Okay, this is the first one. This is like the big colony. It's called Marana, and it is around a K-dwarf star. K-dwarf star. It's actually around 94 Aquarii b. Basically, none of these systems I chose are known to have planets, but I did try and make sure that they were ones that we would not necessarily have already ruled out there being planets, if that makes sense. This one is going to be 94 Aquarii b, and then a made-up planet that I called Marana that is at 0.7 AU. Let's do it! Let's open a file. At work, I use VS Code for all my Python. I guess we're just gonna use this. This is what I did for all of grad school, actually. I just used the IDL. IDL that comes with it. Okay, so we're gonna go ahead and we always start with our favorites. I always start with my favorites at least, and then I'll import REBOUND. Boom, boom, boom. Bada bing, bada boom. It's been a long time since I've used REBOUND. I don't even know. It's gonna be an exercise for me, for sure. Okay. Sim equals REBOUND.simulation. I'm just gonna need to pull up the docs here. I don't remember all the keywords. Oh, that's not right. Okay. Okay, that worked. Obviously we want Python. You can use REBOUND in C. I do not personally know C. That's my bad. I'm actually supposed to be learning it at work, but I have not yet. Whatever, we'll do this one. Okay, that's right. I don't have to do anything for simulation class. I just need to instantiate it. So we're going to add a star, and this star, 94 Aquarii b, has a mass of 0.867 solar masses. And I believe solar masses is the default mass unit for rebound, so I don't need to specify that. I'll bring in the units from AstroPi too. Okay, and then I know that there's going to be a planet there at 0.7 AU, and it's an Earth-like planet. Rather than look this up myself, I'm just going to use AstroPi. I literally cannot type today. So that should give me 1 Earth mass in solar masses, and then I need to give it a semi-major axis, which is going to be 0.7, because AU is the default length unit. What else do I want to put in here about this planet? Does it have any eccentricity? I'll just give it a very mild eccentricity, 0.05. That seems pretty reasonable. And then we will give it a periastron argument. Gosh, it's been so long since I've used rebound. This is embarrassing. I used to be able to do this like without even thinking about it. They do use omega. I couldn't remember if it was spelled out or if it was just abbreviated OM. And I'll just do something random. Let me just print a random number and then use that. I could actually just set a random number generator seed, but I'm too lazy, so. Oh, I need to save it. The Marana system. Let's call it Marana. Oh, module. I don't have AstroPi installed. That's good to know. How do we even install this on Windows? Can you use PowerShell? I really have no idea. Yes! Now, let's try this again. Cool. There's gonna be our omega. All right, so now we have the star and our first planet. I guess we can visualize this. Oh my God, do I even remember how to do an orbital visualization? Probably not. Probably not. Isn't it sad how fast you lose skills if you're not using them? It's kind of a bummer, you know? So we will have an orbit plot of our simulation. I think I just need to, I live kind of close to a busy street now, so it's actually even worse background noise than my old place, so I apologize. Ta-da! There we go. That makes sense. It will go round and round in this two-body problem forever, no issues. But that's not fun, so let's add some more planets. The funny thing about trying to construct a system is that we really don't know what systems look like, to be honest. You would think we do, but we know what our system looks like. But it's very, very difficult to get a picture of what a full exoplanet system looks like because we're not sensitive to the same regions within a system for the same stars in general. And so it's really hard to know what the close-in planets look like and the faraway planets. And then also, especially for faraway planets, the signals are a lot fainter. The periodic signals are a lot longer. So it takes a lot, it's really difficult to do. And so is our solar system all that normal? I think is still an open question. And some of the things about our solar system, like the very small size of Mars, seem to be kind of an outcome of random chance that is not necessarily the most common outcome. So, like, is there going to be a Mars-sized planet in my system? I don't know. Is there going to be a Mercury-type planet? I don't know, because that also, again, something weird happened to Mercury, and to make it mostly iron, and is that a common thing that happens to other close-in planets and other systems? Depends. I actually was working on a project about that when I was in grad school and I never finished it. So sorry, Leslie. I really liked it, but I can only focus on so many things. Let's add a super Earth because super Earths seem to be really common for exoplanets and we don't have any in the solar system. So I think it would be really interesting. Let's make it 5 Earth masses. Where do I want to put this planet? Maybe I'll put it around where the asteroid belt is, which would be around 2-ish AU. I'll make it slightly more eccentric. Is that a valid thing to do? I don't know. Let's get another random number for this. I also do not remember the keyboard shortcuts as well for this anymore since, like I said, I mostly use VS Code at work now. And let's give this one an inclination just of a couple degrees. Let's say 6.5 degrees radians. So that means we also need to give it a big omega, which is the argument of the longitude of the ascending node, which is just where it passes upward through the plane. 4.05. Bada bing, bada boom. Well, let's visualize this first. What? Oh, it's not I, it's probably ink. Ta-da! Ooh, we could add, for orbit plot, you can add, it'll show where the argument of periastron is. So the argument of periastron is just the point in the orbit where it is closest to the star, where its periastron is. So we'll just make periastron 2. Ooh, and we'll make color equal true. Why not? Looks so nice. Now we want to integrate it and see if it is stable. It should be stable. I'd be surprised if it wasn't. I'm not going to integrate it super long just because I ain't got time for that. What even is the... Oh my god, I forgot the command. It is something. Okay. Should have trusted myself here. How long do we want to integrate this for? So the units for time in Rebound, the default units for time are year per 2 pi... No. 2 pi per... I can never remember which way the 2 pi goes, and so I usually just change the units to years because it's easier for me. I just don't remember how to do that. This is really not going as well as I thought it was. There we go, unit convenience functions. It's like, I'm not trusting myself here because I knew that was how it worked, but okay, now I don't have to worry about it. Okay, so we're gonna make times, let's do 1,000 years and just see how long. So for IT and enumerate times. Oh, I should probably save. What should I save? I can just save the semi-major axis. 2. I have been having to use MATLAB at work lately. Not my favorite, but now when I do things in Python, I like I keep typing length instead of len, or sometimes I try and put semicolons at the end of my lines. It's very annoying. I do not like MATLAB. I wish I did not have to use it. Now I will have that. So we're gonna go sim dot. Well, actually, let's save it first because we want to have our initial values. So SMA is 0, I swear I'm not this much of an idiot. P equals sim dot. So that will let us fetch all particles. No, P0 is going to be the star. What did I do wrong? I'm missing parentheses. No wonder. Could have done this using indexing a little bit easier, but whatever. Okay, and then we want to look at what that looks like over time. I don't know what is going on with me today. Because I hadn't defined the simulation yet. Really just embarrassing myself here. I don't know why I thought this was a good idea. All right, let's also time this and see how long it takes. And yes, I know there's probably faster ways to do this. I don't know. I've never used a decorator in my life. So we're just gonna do it this way. Cool. That took very, very, very little time, which is good. Okay, so that means we should be able to stretch this out. Let's try 10,000. Why is this? Oh, because I'm not actually integrating it. Oh, duh. Now let's see how long it takes. It's gonna take longer. I knew that was way too fast. I was like, dang, this is just speeding along. Okay, well, yeah, now let's just interrupt that. Let's go back to 1,000 and see how long that takes. Good, we actually got a real thing. We can zoom in here on this and see if it's actually changing. It's probably not, to be honest. Aha, there you go. This is the scale at which you need to look at it for it to change. This is about a millionth of an AU. So that took less than a second. That's good. Let's try 10,000. Beautiful, very stable. Only took 3 seconds. Okay, we're gonna do one more at 100,000 years. So that took 34 seconds. Ta-da! So we're good with those 2 planets. Let's add another planet. Let me just copy this one. Let's give it a weird planet. Let's say that there's like a gas giant, like a Saturn-size gas giant. What's the mass of Saturn? 95 Earth masses-ish. Okay, so we'll do a Saturn-sized planet. Make it 93 Earth masses. Slightly smaller than Saturn. Where are we gonna put it? I guess the question is, do I want this to be the farthest out planet? I think so. Because whatever made it this inclined is going to be, probably would have brought to the outer part of the system. That's what I'm telling myself. Don't take this as gospel. This is just me thinking of things off the top of my head. We'll call that 6.3. And it's going to be kind of eccentric. And it's going to have 21 degrees of inclination. We do need to get a new 5.86. 5.72. There's our beautiful visualization. We can see the outer planet. It's a little weird. It's a little weird. That was intentional. This should take around a minute or less than a minute. I'm waiting on my classmates, sir. Finished up the last of my Christmas shopping this morning, so I'm gonna mail gifts to my family on Monday. Well, I think my husband's gonna do it for me because he works from home, so he'll be able to go during the day. Here we go. Okay. I didn't save the 3rd planet. I'm an idiot. Okay, so this is why I should have done this in the first place. Let me pull this out of the loop. This will be the length of P minus 1. Here we'll just do, again, the first one is the star, and we don't really care about the star. PJ. Oh, PJ. I like that. Put it on my luggage. The real ones will get it. Wait for another 42 seconds. Oh, index 3 is out of bounds. Oh, because I have to do 1 index down. No, I don't want to do 1 index. That was the wrong one to change. That's the one I have to do 1 index. Fun fact, I actually was literally just wearing this shirt today as I was running errands. I did not pick it out just for this video. I have these really cute Christmas nails that I did, but I did them last Saturday and so they're starting to come off. And I lost this one when I was making dinner today. And I lost these 2 when I was running errands today. So it's very, it's getting a little sad here. Ta-da! Cool. Let's see how this one looks. Pretty good? Well, that's not gonna be our last planet. Let's add one more. We'll add a little one, interior to our habitable planet. Maybe it'll be like 0.6 times the mass of the Earth. How close do we want to put it? We'll call that 0.51. We'll make it a little bit eccentric and we'll make it a little bit inclined, maybe in the other direction. 4 degrees. No, it's a small planet. We'll do 12 degrees. Let's get some random numbers here. There we go. You can see that little planet we added in there. It might be a little too close. Well, we'll see. That's why we're doing it. It's like already getting dark in here. It's 2 o'clock. Okay. Well, look, it is stable. At least on this time frame. You can see that it took longer. Why am I pointing as if you can use the cursor here? It took longer, for sure. Makes sense, there's more planets, and these two are a lot closer together. So the default integrator that Rebound uses is called IAS 15, and it's an adaptive step integrator, which is really nice because you don't have to like think about what the necessary time step is that you want to use, but it also means it can get really slow because it will get smaller and smaller time steps to make sure that it's resolving things. Let's look at this inner one. See how it's varying quite a bit more than the other ones. I think that makes sense. I think that should be stable. I probably should have done like back of the envelope, you know, separation calculations about whether or not they'd be stable. Save me some time integrating this, but whatever. Let's add one more thing. Let's add a moon to the system. Should Marana have a moon? Actually, let's give 3 moons to Marana, but they're going to be small moons. They're not going to be like our moon. Okay, so see if I remember how to do this. Now, normally when you add a particle to a simulation in Rebound, adds it relative to the center of mass of the system. So if you want these orbital elements to be relative to something else, you need to specify that explicitly. So I'm going to explicitly specify that the primary for this orbit I'm adding is the planet. Is it just called primary? We'll see if this ends up working. Okay, this is gonna be a small moon. We'll say like a little bit bigger than Deimos and Phobos. Let's look up their masses. Phobs. Phobos has a mass 1.8 times the mass of Earth's moon. God, AI is dumb. What a great example of how you should not trust those stupid AI summaries. The mass of the Earth's moon is 7.3 times 10 to the 22 kilograms. Phobos is 1 times 10 to the 16th. Okay, anyway. So let's make it about 10 times more massive than that. 2.1 times 10 to the 17th kilograms. And so here's the advantage of doing things with astropy units is that I don't have to fuss about here. I can just be like, yep, yo, I'm working in kilograms now. And then again, you can just convert it to the unit you actually need. Very handy. I really resisted using astropy units for a long time. I don't really know why. I liked Googling unit conversions, I guess. How far away is this going to orbit? I don't know. Again, let's just look at Phobos here. Let's crib some things from Phobos. Okay, so it is at 9,376 kilometers. Let's make it a little bit farther than that. Let's say 27,000 kilometers. We'll do a little bit of eccentricity. How about, I don't know why I made that. Does it matter if I did this consistently between them? No. Am I going to change it? Yes. I got issues. I don't mind either one. It needed to be the same. That's all I'm saying. Okay, let's make it 0.09 and its inclination, let's give it the same inclination as the moon. Why not? Why the fuck not? Ooh, I should see if this will, I have no idea if this is going to be the right size for a solar eclipse. I'm guessing no, because this planet is closer to the sun and I'm making it a smaller moon. But it's a lot closer probably than Earth's moon. I don't know. I'll have to do the math on that one. But not right now. Okay, 5.1415. We'll call that 5.15. We'll call it 5.2. And we're gonna need an omega and an omega. What a weird video I'm making right now. Lovely. Let's see if this worked. I think you can't use orbit plot for this because orbit plot assumes that they're all orbiting the primary basically, or the center of the system. So yeah, you can see here, it's assuming that this object has an orbit. It does not. So they're both right next to each other and you can see these 2 orbits and that's obviously not correct. So there's a whole example on how to do this. I'm just debating if it's worth it. Oh, why not? What else am I doing? Nothing. That's one. Okay, let's go to visualizations. I think to do this, you basically have to pull out the orbit elements. Like it gets a lot more complicated to be honest. But I don't mind. Ooh, I think they maybe updated this because I don't think it used to be like this. It used to be a lot more complicated, in fact. But let's see if this works. I have to remember how many planets I added. I don't remember that. 1, 2, 3, 4. And then that means this one is 5 and it's primary. Let's zoom in and see if that actually worked. I don't think it did. Is it just way too close? Like, sorry, Rebound, I shouldn't have cussed you out. You were working just fine. I did put it really close to the planet. All right, well, let's see it. Let's see how it goes. And then after this, we'll do one more system, and it's one that's actually a real system it's the only one I use that is a real system. Which one is it though? Tycho. Still running. This is gonna take forever. Okay, I might. It's so hard because it's like, how close is it to being done? We're just gonna. Let's do one less, and we'll have it actually. Just so we can keep track. So this goes back to the point about IES 15 and then its adaptive time stepping, because it's going to a really, really short DT, I'm sure, to capture the motion of this moon because it has such a tiny orbit. Am I having regrets about this? Possibly. Okay, let's restart it again. Let's just do 1,000. Let's see how long that takes. Where are we at? 3. Regrets. But now it's like halfway done. I don't want to cancel it now. I can't even go on my phone because I'm using my. What am I supposed to do with myself? I have like 2 minutes to spare. I want to cancel this so bad. I'm a very impatient person. But I'm gonna just deep breath, let it run. This is making me really nostalgic. I'm very lucky in that my day job is very interesting and I do get to do science. And I'm even doing an orbital dynamics project at the moment, but it's satellite orbits, which is very different than planetary orbits. So yeah, I don't mean to complain about that, but I do miss doing research, and I miss running Rebound, and that's right. I just get to run it for fun now, so 80% done. I'm gonna cut this part. We're so close. Ta-da! As you can see, in fact, it is not giving the correct semi-major axis for this moon, but you can see that its semi-major axis relative to the center of the system is going around the planet that is orbiting, which is what you would expect. So that's interesting. Let's look at that. Obviously with terrible resolution because I only did 50 times steps. Not unstable though for 1,000 years at least. That took 262 seconds. Over 4 minutes. Too long. Let's say that's the closest in moon. And let's go ahead and add 2 more moons. Didn't I say 2 moons? Or 3 moons? I think I said 3 moons. So we'll do 2 more. We'll do them at the same time. I'm gonna make one be really small. Let's do 4.7 times 10 to the 15th kilograms. That one will be in between. So let's make that 150,000. Oh, that's 1.5 million. Okay. It's going to be a little bit more eccentric because it's so small and weird. And it'll be much more inclined to. Well, I'll get the omegas in a second. Okay. And then the last one, maybe that'll be a big one. Maybe let's make this like to the 20th. And we'll make this like 6.1. And we'll put this one really far out. Say 232,000. And it'll have a pretty low eccentricity and a very low inclination. I need 4 of these, so I might as well just do them all at the same time. I find one thing that I do when I code is that I do it the hard way a couple times until I'm like, oh, this is too annoying, and then I just do the easier thing that I should have done from the start, as you have seen already in this video. Very small. Okay. Oh no, this isn't radiant. All right. Anyway, sorry. Oh, I just do not shut up, do I? Guess that's why I make videos on YouTube. Okay. These are all relative to the same one, so I should just be able to add them as one. Let's just visualize this first. And we're gonna have to zoom real far in. I'm gonna remember this time. Look at that little system. Oh, it's so cute. Okay, I really did make that interesting. No, I'm gonna move that middle one farther out. Oh, I had the right number of zeros before. That looks pretty good. Maybe that close one is just too freaking close. Let's make that like 67. That looks pretty good. Are they gonna get too close? I don't know. We'll find out. We will find out. This is probably gonna take a while. Well, let's say, otherwise we will see if I remember how to do this. I don't remember how to do this. I'm just gonna look at it. Don't have to memorize things. What is this rotation thing? Oh, interesting. That could be really helpful. Oh, I used to do this manually. Oh, I had this whole function that I wrote when I was in grad school that would rotate a simulation into the invariable plane. Yeah, and there was like rotation matrices, and you had to convert everything to Cartesian units and do all these rotations and then convert it back. This is really interesting. But completely irrelevant. Okay. Not what I need to know. I know how to get the orbital elements, something not around. I think when you can call the orbit thing and you add primary into that. Let's say orbit equals p j dot orbit primary equals p1. And then it's just going to be orbit. Let's see if that works. Just break right there. Ooh. Oh, that's because it's probably because it's empty. All right, let's just make this zeros instead of empty. Perfect. And then these ones down here should have really, really tiny ones because this is an AU. Maybe instead of looking at their semi-major axes, I mean, that's very helpful and all, but we could do their distance from the star. That would be interesting. Okay. I believe in the past you just had to do this by calling the Cartesian coordinates and doing some vector math. It looks like they added a bunch of new convenience functions, so I'm kind of curious about that. No, okay. You still just have to do that. Okay. These. Let's just make these nans so that we see nothing on the plot if we're not requesting it. Let's get the star location P0. Okay, so we're just gonna get a triple here of the Cartesian coordinate. Really, we only need to do that once, so we'll do that outside of the loop. I know how to do this. Sometimes I have to take a second to think. Okay, so it's gonna be the square root of the difference in the x positions squared, and then obviously we're just gonna repeat that. Another 3. Int object is not callable. Perhaps you missed a comma. Oh, I missed a plus sign is what I missed. So here we can see the semi-major axes, actual ones. So this is relative to the planet for our moons down here. Beautiful. And we can see their distances, which if we zoom in, yeah, okay. And now we only did that for 2 time steps. So let's get rid of that. Actually run this and just accept it's gonna take forever. I can read. I've been reading this for like 2 years. Where'd my bookmark even go? Uh-oh. Oh, it just fell out. It got caught. Oh, the end of it got caught. And it untied the knot. Well, anyway, I've been reading this for like 2 years, and it's not like I dislike it. I know so many people love this, so I don't want to say anything like negative. I find he is very, a little smug, I would say, is maybe the impression I get, and a little sexist. So, see if we can tie this knot again. How are we doing on time? Ooh, we're over 60% done. Okay, but I will need to figure out where it was at. Okay, what do we got here? Yay! All right. I'm trying to even remember what planets I had. I'm getting so confused. Okay, so the green one was that weird giant we put on the outside of the system, and you can see its semi-major axis is not changing, which is good. That means it's, stable orbit, but its distance is changing a lot, and that's because we gave it a pretty high eccentricity, so it's getting closer and farther away from the star. And then the second one, oh, that's the super Earth. That's the super Earth. Again, same thing. What eccentricity did we give that? 0.1? Seems like a pretty big, I guess not. If we zoom in, we see this is our really close-in planet. You can see some structure in its movement there. And then this is our habitable planet with its moons. And you'll be able to see, we probably have to zoom in really close here, that obviously they are very close to the planet the whole time. And if we look at their semi-major axes, way down here, they're stable. This is only 1,000-year time frame. So, it's more than 1,000 orbits of our habitable planet because it's at only 0.7 AU. Don't have the patience to do it for longer. So I was going to do one more system, but this has already been pretty long. I've been doing this for 1 hour and 20 minutes. Is anyone even going to watch this? Oh, hell, let's just do another one. Why not? Okay, let's do a new file. I'm going to want these things. Okay, now this one is the one I said is actually based on a real system, real planetary system. And that is because the habitable planet in the system It's not a planet, it's a moon. And so it would fall into the same criteria I had where it is not something we would have been able to detect already and, but is feasible that we could detect in the future. So that's what this one is. And it is a circumbinary planet. So it's a habitable moon around a giant planet that's a circumbinary planet, which means that it's orbiting 2 stars at the same time. So what a really interesting system. It's called Kepler-17. Here we go. NASA Exoplanet Archive should have the data we need. Oh, and its mass. Mass. Is this actually Kepler-17? Am I incorrect about this? Kepler-47. Oh, it's fine. I'm doing my best. So, there are obviously 2 stars in the system because it's a circumbinary thing. That's not helpful. Is this also the wrong system? Yes. Okay, good. I'm not crazy. I was really doubting myself there for a minute. Okay, so let's add the stars first. I don't know why the Exoplanet Archive was not quite giving me the information I need, but whatever, we'll just take it from Wikipedia. First, we will make a simulation. Rebound that simulation. Huh. Then we'll add our first star, 0.957.342. Orbit is a semi-major axis of 0.0108145. Eccentricity of 0.0288. Inclination of... Oh, so the inclination here is... Yeah, it's like kind of in a different frame. So I think what I want is actually 90 minus this inclination. And I'm pretty sure we probably don't have an ascending node for this. So I'm just going to leave it. And then 26.3. Oh, again, let's make that into radians. Radians? Did you say radians? No. Which is funny because you say rad as the abbreviation. There we go. Now we got our stars. Now hopefully the Exoplanet Archive will be helpful and give us the planetary information. 3 planets in this system that we know of. First is 2.07.2877. I guess that's everything. Now, notice I didn't have to specify the primary here because it automatically adds things relative to the center mass of the system. So it will automatically add it as a circumbinary planet. You would have to specify the primary if you wanted to make it a circumstellar planet. That's planet B. Let's do planet D. Right, and then C. So the fact that I did not provide the ascending node means that they're all going to have ascending node, I think, of 0, which means they're all going to be in the same... Their ascending nodes are going to line up. It's fine. That's actually kind of difficult information to get from a transiting planet. So now we have all of our things in there, all the known things in there. And I want to add my planet, moon. Sorry, my moon. Question is, where did I even do that? Because I did come up with a distance for it. Maybe I didn't. No, because I think I decided it was tidally locked, which means 5.877 is the number of days of its period. Of its period around the planet, not its period around the stars. Oh, so crazy. Okay. So this one is going to have sim dot particles 0, 1, 2, 3, 4 as its primary. I'm going to pass a period just because for whatever reason that's apparently how I calculated this in the past. I don't even know. I don't know, y'all. Okay, and this is going to be in days. I don't think I had any other properties written down for this planet. I'm going to assume its eccentricity is like nothing. Inclination relative to its planet is going to be very small. Do a random... See if this works. So I honestly do not remember where I got this period from. I'm not even sure if it's realistic. We'll find out. So we want particles 1, 2, 3, 4. Wait. 1, 2, 3, 4. Yes, okay. And then particle 5, its primary is 4. One thing I'm not sure is how to make the second star show up as a star on... I don't know. Yeah, because I want to show those two... I don't know. All right, let's look at this. There's our beautiful habitable moon. Okay, what I could do is dig into the guts of it. But that's fine. That's just a visualization. It's working fine. Everything under the hood will work fine. Okay, let's get our thing going here again. No need to redo all that. Let's see how long this takes. Oh, the thing is when I calculated the distance, I did calculate it relative to the first star, not relative to the center mass of the 2 stars. All right, look at these beautiful Oh, that's not good. So a negative semi-major axis means that it's an unbound orbit. So this is saying that I started it on an unbound orbit. Oh, I guess that's because it's giving it relative to the, I don't know, let's look at the distance. I think that'll make more sense. So the red is the planet, the actual planet, the purple is the moon, that is our planet, so to speak. That makes sense. We could do a much finer simulation over just like a couple orbits of the thing. If it has a 5.8 day period, we could do like 12 days, like that. And we'll do like, I don't know, 1,000 or something. Really tiny little steps here. All right, so this is the distances. This is semi-major axis. Yeah, whatever, ignore that. Okay, so this is the distances from the central star, And yeah, you can see, you know, it gets closer, it gets farther away. Looks pretty nice. I guess what we could do, plot. We'll just do X and Y, even though obviously we know that that's only going to be part of it, but okay. And then we'll do this for each of these. Sure, they're all the same color. This might be too many times. I don't know. We'll just see. All right, look at this. So now we can see in 2D. So these are the two stars going around one another. And this is the innermost planet. And this is the middle planet. And then this is our outer planet and its moon. That's kind of cool. Yeah, what I could do is change the alpha over time. Oh, let's try that. Okay, so alpha should just be I divided by 1,000. Okay, and let's go ahead and let's just make, I'm just going to do this by I. I'm too lazy. I can't be bothered. Okay, so we'll just call the limit. Just want it to be symmetric. Probably don't really need to do that, but maybe I wanted it. Let's go a little bit bigger. There you go. You can see, so it's the more faint it is, the farther back in time it is. So as it goes forward in time, you can see it getting more solid. Pretty cool. What if we did this for longer with fewer steps? I don't know. Let's just make this a year. Let's see how we go. That's weird. That shouldn't be empty. Oh, I did not do that. See, this is why you shouldn't hard code things. I should have just done lane times. No. I was trying to save myself 2 seconds. Oh, these limits are not good at the moment. Oh, I didn't move this into the center mass. Okay, let's do that. After we add all these particles, we'll do sim move to I think that's what it's called. Ha, there we go. Okay, this is making a little bit more sense. And you can see there's like multiple orbits here because it's getting like darker as you go around, at least for these inner ones. Whereas for this outer one, you're really only kind of seeing one mostly orbit. And here are the stars, both in their little orbits. But yeah, so you can see that every, orbit it went through, it was a little bit farther along in its orbit when it got plotted. Okay, let's go back and look at the... Okay, this one I'm doing it, even though it won't matter because I think this is going to be the last time I do this. What parenthesis was never closed? Oh, that one. Here we go. Let's see these guys. Ooh, pretty cool, I think. I don't know. Maybe no one else thinks this is interesting, but I think it's fun. And plus, now I have some more information about these systems and what to write about, so that's exciting for me. Anyway, I think this is going to be it for today. I hope you had some fun and maybe learned a little bit of something about how to use Rebound. Probably not. Or at least just had fun hanging out. I had fun. So thank you so much for joining me, and I will see you guys again soon. Happy holidays. Wish you all the best and Happy New Year. Bye.